Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the final one in the second series on impulse and momentum, and it's about impacts with a smooth plane. The story so far: the coefficient of restitution E is a measure of the elasticity of a collision, and it's a property of the combination of materials. So we have the usual summary that E is the separation speed over the approach speed. E lies between 0 and 1 and it's dimensionless. E equals 0 is an inelastic collision where the two bodies cohere. That in the case of collisions with a plane would be like a snowball sticking to a wall. And E equals 1 will be a case where you have perfect elasticity. Kinetic energy is calculated for all the objects together, so if we're talking about energy loss, it will be final kinetic energy minus initial kinetic energy. Here's a first diagram representing an object bouncing from a wall. So the velocity of approach, that is to say the velocity immediately before impact, is u meters per second towards the wall, perpendicular to it, and immediately afterwards it's v meters per second away from it. And E is our separation speed over approach speed, and so that will now allow us to relate the u and the v to each other, because if it's a fixed plane we can take it that the velocity before and afterwards is 0. You can't apply the conservation of momentum here because there's got to be something fixing the wall. It doesn't move away, and that means to say that there are external forces acting which do have impact in this particular collision. So let's look at a simple case first. If we imagine the question as usual, what's the half equal to? It's the velocity of separation. Well, that's v clearly. Speed of separation is v over the velocity of approach is just 3, because in both cases, although we don't show it, you've got an initial and a final velocity of the wall of 0. We'll just put that in for completeness, but normally that's not shown at all. So that tells us that v will equal 3 over 2. You've halved the velocity by that particular impact. So there we are. We end up with the conclusion that the velocity afterwards, the rebound speed, is 1.5 meters per second. Now let's look at a more complex situation, but much more typical of the kind of thing that occurs of interest. A ball of mass m kilograms is released from a height, and you're given the coefficient of restitution between the ground and the ball, and asked to find the height after the second bounce. So we've got two collisions here. It's a more complicated problem. Now that diagram is actually meant to represent with the horizontal axis as a time axis, so that you can imagine that's showing a trace of what the ball's doing. It's actually moving up and down vertically. So although the picture might suggest it's moving sideways, that's not the case, because this is actually a time axis. Righto. So how do we deal with that? Well, the first thing to do would be to recognize that we need to put a velocity of approach in for the first collision. That's not very well drawn, is it? And a velocity of separation, bounce back again, and similarly for the second collision, and for the bounce in, and for the approach velocity and the bounce back velocity. So we need to put letters on for those. So there we are. I've given those as a sequence of u's. Now that allows us to discuss the problem, but the discussion is quite lengthy, because in the first instance we need to consider how to convert the height, which is given as 12.8 meters, into a speed of impact. Now that can be done two ways. You can do it by suvat. You've got g equals 10, so v squared equals u squared plus 2as will do it. In this case I'm going to use energy. The numbers will look the same. It's just a matter of whether you include the mass as a factor and the half for the energy. So we'll look at that then and see what the first calculation is. We've got our u1, that's what we're looking for, that's what we're trying to find. So we've got a half m, I don't really need that there, do I? Let's take it out. So we've got, by conservation of energy, the final kinetic energy on that first section is equal to the potential energy lost. Notice that the m cancels out, so we end up saying that u1 squared is twice gh. And that works out as 256, so when we take the square root we get 16. It has to be positive, of course. So we're saying that the approach velocity at B is 16 meters per second. Now, given that the ball and the ground have a coefficient of restitution of 3/4, that immediately tells us that our bounce back speed will be 12. So there we are. The first bounce, having started with a 16, gives us a 12 for the bounce back. Now at this stage we can do two energy calculations. We could use that speed to work out how high the ball goes by conservation of energy, but what's the point? We're not asked. What we can say is that energy will be conserved over this section of the motion, and that will mean to say that the kinetic energy initially is the same as the kinetic energy finally, and that boils down to saying that u2 is equal to u3. So our next section is to say that u1 is 16 and u2 is 12, and then finally that u3 is 12 as well by the conservation of energy. In the final section we need to repeat the first calculation, but backwards as it were. We need to find what the bounce back velocity is and turn that into the height by using energy once more. So if the approach velocity for the second collision is 12 and the coefficient of restitution is 3/4, that turns into a bounce back velocity of 9, 3/4 of 12. So that's the 9 that we need to use in our final energy calculation. We're going to say that the kinetic energy at C is converted into potential energy at D. So that will tell us that, given our summary of the story so far, that a half m u to the fourth equals mgd, and just as in the first calculation the m cancels out. So that's kinetic energy is equal to potential energy on that final section. Potential energy lost essentially is equal to kinetic energy gained. At the top of the bounce, it's going to have no kinetic energy. So that means to say that we'll get, using g as 10, that d is a 20th of 9 squared, and that works out at 4.05. So our final velocity is 4.05. It's an interesting example here of how, given that it's a 12.8 meter drop to start with, you really can have no idea what this final velocity or final height's going to be. It has to be through that set of complex calculations, systematic calculations rather than complex, and so we can get our final answer as a result of a series of stages. So the height reached after the second bounce is 4.05 meters. That's our answer in context with the units. Well, that concludes the video on successive impacts with a plane. It also concludes the series on impulse and momentum section 2. After this comes more on dimensions, and I look forward to being with you to explore that.